Welcome back to our series on alkyne reactions. In the previous video, we explored oxymercuration, which hydrates an alkyne following Markovnikov's rule to produce a ketone. In this video, we look at the complementary reaction, Hydroboration-Oxidation. This method also adds water across the triple bond, but with opposite regioselectivity. Our focus here is the reaction of the terminal alkyne, Propyne, using a sterically bulky Dialkylborane, followed by an oxidative workup with hydrogen peroxide and sodium hydroxide. Starting with Propyne, the reaction proceeds in two main stages. First, the bulky borane adds across the triple bond. Unlike oxymercuration, this reaction exhibits 𝑎𝑛𝑡𝑖-Markovnikov selectivity. The bulky boron group attaches to the less substituted terminal carbon due to steric hindrance, while the hydrogen adds to the more substituted carbon. After the oxidation step, the boron is replaced by a hydroxyl group. This intermediate has a structure corresponding to a terminal enol, also called vinyl alcohol, but it is not isolable and rapidly tautomerizes to the aldehyde. Because the hydroxyl group ends up on the terminal carbon, the rearrangement furnishes propanal rather than a ketone. Note: under basic conditions, the intermediate briefly exists as an enolate-like species, which collapses quickly to the aldehyde upon protonation. The mechanism is divided into the hydroboration stage and the oxidation-tautomerization stage. We will follow the transformation chronologically. Stage 1. Hydroboration. Step 1. Syn-addition of dialkylborane. The reaction begins with the concerted addition of the BH bond across the carbon-carbon triple bond. This step is stereoselective. It is a syn-addition, meaning the boron and hydrogen atoms add to the same face of the pi bond. Simultaneously, it is highly regioselective. The large alkyl groups on the boron force it to add to the less substituted terminal carbon C1 to minimize steric hindrance, while the hydrogen adds to C2. Importantly, unlike simple borane, a dialkylborane contains only one BH bond. As a result, the reaction stops after a single addition, yielding the desired monoalkylborane intermediate. In practice, sterically bulky reagents such as dicyamylborane and 9-BBN are commonly used for this purpose, as their size further enhances anti-Markovnikov selectivity and ensures clean formation of the desired intermediate. Stage 2. Oxidation. Step 2. Oxidation and enolate formation. Once the alkylborane is formed, basic hydrogen peroxide is added. The HOO-, hydroperoxide and ion attacks the boron atom. Through a series of rearrangement steps involving migration of the carbon-boron bond onto oxygen, a 1,2 migration, and subsequent borate departure, the boron is cleaved off. This functional group replacement proceeds with retention of configuration at carbon. Under the strongly basic conditions, the initial oxyanion remains deprotonated and is best represented as a resonance-stabilized enolate. The enolate is best depicted by two principal resonance forms, one bearing negative charge on oxygen and the other with a negative charge on the alpha carbon, C2. Note on alpha carbon. The alpha carbon is defined as the carbon atom immediately adjacent to a key functional group, such as the carbonyl group. In this mechanism, C2 acts as the alpha carbon position in the resulting enolate intermediate. Step 3. Protonation. Leading to the aldehyde. Water molecules in the solution serve as the proton source. The predominant pathway is C-protonation, in which the nucleophilic alpha carbon, C2 resonance form, accepts a proton from water. This step leads directly to the formation of the aldehyde upon collapse of the enolate. This pathway is favored both kinetically, the carbon center is the stronger nucleophile in this system, and thermodynamically because it produces the lowest energy product, a stable aldehyde. Minor pathway, O-Protonation, and subsequent tautomerization. Alternatively, the O-Protonation pathway occurs when the oxygen atom accepts a proton, initially producing the terminal enol. Although O-Protonation is often kinetically competitive in many enolate systems, the enol formed here is highly unstable relative to the aldehyde. Even under basic conditions, rapid proton transfers promote tautomerization, driving the equilibrium strongly toward aldehyde. Thus, regardless of whether protonation occurs at carbon or oxygen, the reaction mixture ultimately converges to the thermodynamically favored aldehyde. For internal alkynes, hydroboration-oxidation uniformly produces ketones. However, the regioselectivity of the transformation depends on whether the two alkyne carbons differ in steric bulk. In substrates such as 2-butyne, both carbons of the triple bond are electronically and sterically equivalent. Because boron has no regiochemical preference, hydroboration-oxidation furnishes a single ketone product. When the two alkyne carbons differ only slightly in steric bulk, as in 2-pentyne, a bulky borane cannot clearly distinguish between the two sides. As a result, the reaction often produces a mixture of regioisomeric ketones, reflecting weak regioselectivity. In contrast, a substrate such as 4,4-dimethylpent-2-ine exhibits a pronounced steric imbalance. The heavily substituted side strongly blocks boron approach, causing the bulky borane to add preferentially to the less hindered carbon. Thus, the reaction affords a more regioselective ketone outcome. Let's summarize. Step 1. Bulky borane adds to the alkyne in a concerted 𝑠𝑦𝑛-Addition, placing boron at the terminal carbon. Step 2. Basic peroxide attacks boron, triggering a 1,2 migration that replaces boron with an oxygen ion, forming an enolate with retention of configuration. Step 3. The enolate undergoes 𝑐-protonation as the major pathway, directly producing the aldehyde. Any enol formed via O-protonation is rapidly tautomerized, driving the equilibrium completely to the aldehyde. Let's organize by keywords. 𝑎𝑛𝑡𝑖-Markovnikov selectivity ensures the oxygen ends up on the terminal carbon, driven primarily by the steric bulk of the boron reagent. 𝑠𝑦𝑛-Addition describes the stereochemistry of the initial BH bond addition. Aldehyde synthesis emphasizes the utility of this reaction for transforming terminal alkynes into aldehydes. To wrap up, those who wish to deepen their understanding of alkyne hydration are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.